I know she just went to bed an hour ago. So these are tests you've already had. But this is practice test 1. This was the final 3, and I think we're working on, or this might be 2, I told that one. But in any case, this is the one I'm working on for class. You have all 3 of those, it may be nice in a 12-kind of way to have them. All right, so we're gonna move forward here and go through this part of the multiple choice. As I keep saying, I've been harping, even though I don't play a harp, on this, because if you can get through the multiple choice covers the entire curriculum, okay? And what you see in multiple choice, you're going to see in part 2, okay? You just got to keep hammering on it. I'm a big believer of that, so hopefully you've been doing that and spending time with me online. Sounds kind of creepy, but let's continue. So in 26, the reaction represented above, this is, again, the multiple choice of the 2014, or I should say practice test, whatever I call it. Yeah. So in this reaction, what do we have? We have the number of permanganate ions that must be equal to which of the following. Okay. So in the reaction represented, the number must be, well, okay, so we've got a 1 in front. Nothing in front implies a 1. Okay. And so what are the ratios here? So it's going to be something to something. So if I look at my choices, in the reaction represented above, the number of permanganate ions that react must be equal to which of the following? Well, if I look at iron plus 2, and there's a 5 in front, all right, it's a 1 to 5 ratio, so this has to be 1/5 of the iron, okay? And that's all that really that problem is. Yeah, that's a 2000 right there. You can that one. So there isn't much to talk about here other than realizing that this is basically straight stoichiometry, and we're dealing with a 1/5. So this is 1 and this is a 5. So the ratio is that 1/5. And if you're ever to do a type of question that is going to pop up in this multiple choice, as with most tests, you're going to see a limiting reagent problem. You know, like for instance, if they were to give you 20 moles of iron plus 2, and they were going to give you, let's say, 20 moles of both, and you said who the limiting reagent is, knowing it's 1 to 5, I kind of start with the big guy, the big number here. This is going to represent what? All of it, right? So that's 5. So if this is the 5, then I need only what? 1/5 of that. So 1/5 of 20 would be 4. So you would use only 4, and we would use all 20 of these, and this would be minus 20, and this would be minus 4, and we can clearly go fast and say, okay, in this example, iron plus 3 is the limiting reagent, okay, because of the 1/5 as much. So that's all that is. The other choices here don't have the right ratios. 1/2 the H2Os, I'm not sure how that would work as 4 there, and the other choices B and C make no sense because they have the ratios mixed up. It's not going to be 8 times the number, it's going to be 1/8, okay? And then not 5 times, it'd be 1/5. So that's how that would go. All right, so again, if you were to, if you still don't see this, and I think most of you guys do, okay, getting rid of the permanganate, you would have 1 of them for every 5 irons. If you're doing stoichiometry, you'd put the permanganate on the bottom so that it would cancel, okay? And you can see that this one's going to be, if you're going to go to iron, 5 times as much, and if you're going to go backwards, it'd be 1/5. I think I've talked about that enough. So 27, take the easy questions where you can. All right, so I'm just jumping all over the place. So 27, we've got a graph of absorbance. If you haven't already figured out, they love spectrophotometry, okay? So they got concentration. For those that forget, you've got this cuvette, right? This little plastic little guy, and we're putting something that has some color in it for all the reasons we've talked about this year. And if it's got color, we shine some light with a certain brightness through the cuvette, through that path length, and there's a detector, and that detector basically measures what's the missing light, okay? And the missing light is due to what the chemical is absorbing. So as the absorbance goes up, the concentration goes up. We also have this little formula that's been popping up. A equals ABC. What this means is the absorbance, the amount of missing light, because the chemical is absorbing it to get excited, or in this case, to give off a color because absorbing wavelengths of light, is equal to that absorbance constant times the path length that we used 1.0 centimeters. That's the length through the cuvette, and this C is concentration. So clearly, as concentration goes up, there's going to be more missing light because there's more chemicals to absorb it. So in any case, a little quick review of spectrophotometry. I'm having a tough time scrolling down. So they said they prepare 5 solutions of copper sulfate, different concentrations, filled 5 cuvettes, and they get the data above, which you can clearly see is rising, okay, as the concentration goes up. Now, you'll notice there's one data point that's not really following the trend. It's an outlier from the other data points, and they're asking you what's the possible scenario for that. Since we've done the lab in many ways, this should not be a big deal, okay? What's the scenario? Well, the cuvette into which 0.600 molar solution was placed had some water droplets. Now, if there's some water droplets, would that diluted or concentrated? Diluted, which means the absorbance would be higher or less? Less, because if it's A equals ABC, there's less concentration if you had some water, so the absorbance would be lower. So A makes no sense. Okay, the cuvette into which you add this was filled more than the other cuvettes. Having more of it, does that change the concentration? No, the molarity is going to be constant, the volume is going to increase. Yes, there's more moles, but the concentration per volume stays constant. So that wouldn't make any sense. The wavelength setting was accidentally moved away from the maximum absorbance, which means you would actually have a lower absorbance. If it's stuck on a higher setting and you lowered it, you would get a lower. Remember, that point is above the line. So process of elimination, D is the answer, and D is the answer because the cuvette used had not been wiped clean. Maybe their fingerprints were on the cuvette, which means the light had to pass through what? Not only the solution in the cuvette, it had to pass through whatever oily film you had, okay? So there's more missing light because there's more stuff to go through, including the dirty cuvette, and that's why you had a higher absorbance. But in any case, that one is D, all right? Again, they love the idea that we are using spectrophotometry. I would think you're going to see a question, mass spectrometry. We did not do, but we definitely talked about it and looked at it. Okay, rate law. All right, 28. Reaction is experimentally determine the rate law above. So we have the rate law to be first order. There's nothing in front, so first order it is. A chemist proposes 2 possible mechanisms, which are given below. Based on the information above, which of the following is true. Now, the first thing I do with mechanisms, and sometimes they do this in part 2, is they want you to stoichiometrically prove that's a possibility. Now, what they want you to do there, and even though they're not doing it in this case, it's a good idea to do this because if they're trying to pick between mechanisms, there might be a mechanism that doesn't balance off to the overall. So it's really a good idea to see if, in fact, both of these will, when you cancel out all the either catalysts or the intermediates, that they will equal the entire compound. So you can see that this is 2x, this would be an x, and this x would go bye-bye. This intermediate would go bye-bye, and you can see that we're left with the exact reaction we have up here. And if you were to do the same thing over here, 2x, 2x, let's see here, xy, xy, and then you have y, why not? Okay, and then we have, what other intermediates am I missing? Okay, this guy. So we can see that in both examples, both of these, okay, stoichiometrically come out to the overall. And sometimes in a rate law problem, even though this one is not asking for that and it's not applicable, okay, I'd like to go over those things. In a part 2, they could say, hey, prove that this is the rate law based on stoichiometry, and all they're asking you to do is to cancel out to the overall. All right, so in this case, they both do that. So that's not the issue. So the issue is, if it's first order, how in the world do I realize which one is first order? Okay, well, if I look at the mechanism one, I'm going to get rid of this canceling stuff here to make my life simple, although it's very complex. Okay, not as complex as Alex, but in any case, all right. If you look, what would give me first order? First order with respect to x2. Notice y2 is not in the rate law. Why? Enough y jokes. But
Probably.
that could be, but better yet, it maybe has a rate order of 0. So it's not given. If it's a rate order of 0, it has no effect to the overall mechanisms because it's not in the slowest step. So both of them are not showing y2 in the slowest step, which is a good thing. If something is a 0 order, they're not going to write it because it's not in the slowest step. You still need it. So both of them show that's a good thing. So the slowest step just has the x squared. And because this is called an elementary step in a mechanism, the step that is called the rate determining step is the slowest step. And that is called an elementary step. We get our rate law directly from the slowest step. And coefficients are never going to be the exponents unless we know the reaction is a single step. Since this entire rate law is based on this single elementary step, okay, then we can use this coefficient of 1 for both of them and make it into the order. So again, both of these mechanisms are showing the slowest step, only having x2, not y2, because y2 is a 0 order, it's not written, so it's not part of the elementary step that basically the whole mechanism or reaction process depends upon. So I find the slowest step, I use the coefficients of the slowest step because it's elementary. Both of these are applicable. We can't know definitely which one, but we can definitely say that both are possible. So both mechanism and 1 and 2 are consistent with the rate law. Why? Because the slowest step has the coefficient of 1, and the y2 is not in the slowest rate determining step. Okay, moving forward, 29. Now this one, a lot of people got wrong. Okay, these little diamonds here, multiplication here. Now this is a great little question because I'm seeing this pop up often again. I want to remind everyone that when you have reactions that just like we did above with a mechanism, when you have an overall reaction, the overall equilibrium constant is the product of the individual K's. You say, well, Mr. Grodsky, where did we ever do that? Well, we did do that in derivation. I showed you NH3 in water. That's a weak base. It pulls an H away from the water, ionizes it, makes the hydroxide, and it makes the NH4 plus. And this would have a Kb. Then I took the conjugate acid of this and had it in water, NH4 plus in water. And what did it make? Well, this gave an H, it's a Bronson-Lowry acid, so this becomes H3O plus plus NH3. And this would be the Ka of the acid. And you notice, when I cancel everything off, what am I going to get? Okay, I'm going to get two waters doing what? Breaking apart into the hydronium ion, the acid part, and the hydroxide, which by the way equals what? What is this reaction? Kw. And what we learned? Kb times Ka equals Kw. So I did teach you that equilibrium constants of individual steps will equal the overall when you multiply them if they what? if they cancel out to the overall process. That's important. That does pop up. Equilibrium constants are multiplied together. Kind of like a little S law with them. All right? So let's get rid of this, okay, and talk about what the problem's all about. I'm not sure why I got rid of that, but I am told. Now, question is, what's the overall? The overall I have to look at very carefully. Notice there's two HFs. There's only one HF here. Okay, there's two H pluses, only one H. Okay? For these F negatives to cancel, doesn't this have to be a 2 here? So really I have to do what to the second step? Multiply by 2. I had to realize that. Now everything is going to cancel, and I have the overall reaction. So notice, this K2, the equilibrium constant, was based when these coefficients were 1. That's a big, big understanding right there. Okay? This equilibrium constant was 1 times 10 to the 3 when these guys were 1. Let's just, for fun, it is a lot of fun, to write the equilibrium expression for this reaction. It's going to be the product, HF, okay? It was to the first power, and it was F negative to the first power times H plus to the first power, and it equaled this number, okay? Now, when I times everything by 2, now the coefficients are what? Right. Now they're squared, correct? Coefficients become exponents. So what is this number, 1 times 10 to the 3? It's really, what's the number there? Yeah, it's 1,000. So let's write the 1,000.
Thanks, Sam.
Feel free to. So we've got our K2 equal to 1,000. Now I'm going to try to make some sense to this for me. I'm going to make this equal, okay, to 1,000. And one way I can do that is what? Make the top number 1,000 to the first power, right? And the bottom number is equal to what apiece? 1 apiece. I'm just going to make my life easy. So that's a fictitious way I can make 1,000 in my head. Because I got to understand this. Now, what just happened though? By timesing this by 2 and the coefficients becoming 2, now everything is what? Squared. So this 1 squared times 1 squared, that's pretty simple. What's that? 1 times itself. Put that in your calculator. And this squared is, well, 3 more zeros, right? So this is 1 times 10 to the 6th over 1. Put that in your calculator. It's 1 times 10 to the 6th. So K2 becomes 1 times 10 to the 6th. Okay? And now what we're going to do to get the overall is multiply. We're going to multiply K1, which is 2 times 10 to the negative 6. And I'm going to times that by my K2, which is 1 times 10 to the negative 6. Okay? That's all I'm doing is multiplying my K's. Now that I know my individual K's.
Positive 6 for the second one.
Okay, yes, sorry, positive 6, thank you. All right? So when we multiply numbers with exponents, what do we do with them? Add them. So 6 plus a negative 6 gives me 10 to the, which is 1. 2 times 1 is, so K1 times K2 equals K3, which is equal to 2. Is 2 greater than 1 or less than 1? It's greater than 1, which means the products are favored, which means you have products. So back to the choices. I know K3, okay, is greater than 1. And I know it's thermodynamically favorable. Why? Why do I know it's thermodynamically favorable? If products are favored, that means it's going forward to produce products. Absolutely correct. You have to understand, when your K is bigger than 1, your delta G becomes more negative. Okay? We used this formula way back when. Delta G, okay, is equal to what? Negative RT ln of what? K. So as the K becomes bigger, positive 1, it maintains this negative. This becomes more negative for the forward direction. Okay? All right. Lot going on there. A lot of people got that wrong. A lot of times, guys, they'll give you questions where all you've got to do is multiply your equilibrium constants. But this was a nice little spin. Remember, this was a question that was designed for you to get wrong. And if you did, so be it. If you understand this now, great, because if you see a question like it in part 2, maybe you can handle it. There's a lot more to get right. You get this one wrong, I can see that. A lot going on here. Okay? Moving forward. Maybe. Okay. This one you should not get wrong. First of all, we're talking about H bonding here. Little AP Bio questions sneaking in. Okay, AP Chem, liking it a lot. Okay, nitrogenous bases on the DNA backbone. Not feeling the love like I thought I would feel about it, but hey. All right? All right, now listen. H bonding for the millionth and one time only happens with FON. Fine. Following H bonding. Now why? These guys are electronegative enough. They're the most electronegative atoms. They have the greatest effective nuclear charge for their atoms and their sizes. So because of that, what they do is they pull that pair of electrons between the H and one of these guys so close to it, what it does is it dangles what's left over. And what's left over, okay, when you pull that pair of electrons away from it so much, is just a proton. A hydrogen is one electron, one proton. So if these guys are really small, what you have is a proton dangling out there. And that becomes very positive. All right, let me just get rid of that drawing because it's not going anywhere good. Now, that being said, let's look at our choices. Which one is showing correct H bonding? Is this an electron deficient H? Carbon and hydrogen have almost the same electronegativity, so that would be incorrect. That would never H bond, that's right. Okay, I was just checking bond. B, let's see what we got here. Another non-what? Electron deficient H. That's not an FON. That's not going to H bond. Not going to happen. Okay, B goes bye-bye. Looking at C. Okay, I've got another non-electron deficient H here. This is not going to H bond. It's not going to dangle that proton out there. They're sharing electrons almost equally. So process of elimination, D is the answer. And you can see that this N, which has a little bit positive because of that proton dangling, is hooked up to an N. And this also bonded to the N. So this is the H bonding that's correct. Okay, so duh, D is the answer. All right, easy question in my opinion. Okay, here comes what? Ooh. Positron emission spectroscopy questions. You're going to have these peaks. You're going to have what? Binding energy. All we're doing in this type of a question is we're taking a sample. Okay? Basically, using the photoelectric effect, we're shooting X-rays at the sample. High energy photons. Some electrons are emitted. Okay, so electrons are emitted. Now you should know why they're emitted. If this is the energy of the photon. Okay, there's two parts. There's the binding energy that we overcome, and the rest of the energy is to do what? Measure the kinetic energy of the ejected electron. So what we do is measure the kinetic energy in photon emission spectroscopy. We measure how much by how many. Okay, by the way, we use a charged tube. Okay, I love explaining this because understanding how it works really makes you understand the question. These are negatively charged tubes, so the electron repels them. And the ones that go faster, okay, are not affected by the charged tube as much, and they can hit a detector. The ones that are going slower are repelled more, and they don't go as far. And we can measure how many of these are hitting the detector and the relative distances. But the bottom line is, the faster we go, the higher the kinetic energy, right? The less the binding energy. Okay, so if I've got something with a lot of kinetic energy with the same photon, the binding energy arrow's got to be less. So essentially what we're measuring is how much energy to separate these electrons. Okay? And if you notice, binding energy usually increases as you go this way. So this peak, which is showing a lot more electrons because it's higher, is showing a much higher binding energy. Which means these are electrons that are held what? Closer to the nucleus. This peak showing a lower binding energy for another 1s, they're telling you this, is probably held much farther. Easier to remove electrons in shells that are what? Farther away, because they feel the electrostatic attraction less. So that's all that was. I know you probably didn't need the full explanation, but hey, I'm tall. All right, 31. So a sample of carbon and fluorine was analyzing using the X-ray photon emission spectroscopy. The portion of the spectrum shows the 1s peaks for both. Which of the following correctly identifies the 1s peak for the F atoms? All right, we should know in our reference tables, okay, somewhere I don't have my reference tables out, but in my reference tables, I know that fluorine, okay, is over to the right, right? And we have, let's say, a boron, carbon, nitrogen, oxygen, and fluorine in the second row. And then, of course, we've got our neon at the end. Okay, this is atomic number 9, atomic number 10, atomic number 8, 7, 6, and 5. And what do we know in the same, if you're in the same principal energy level, same row, it's all about the nuclear charge. So fluorine's got more protons in the same energy level. It's got a higher nuclear charge, higher effective nuclear charge. So therefore, it's going to be a lot tougher to remove what? Fluorine's electrons at the 1s level. So we would say, which identifies the peak for the F, we would say peak X. This is peak X right here, okay, because F has a greater nuclear charge than carbon, and therefore the electrons are held tighter to the nucleus. And that's the reason why fluorine has a higher, by the way, ionization energy, okay? So that's why answer to 31 is B, okay? Greater nuclear charge, all right, or effective nuclear charge, however you want to talk about it. Okay. So 32, one of those questions where it's, you'll see definitely something like this Monday where they're going to give you definitely a group of questions on one area. Okay. In a titration experiment, H2O2 reacts with aqueous permanganate. Okay, dark purple is added to a beer of colorless acidified H2O2. La 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 la. Now, endpoint is that pale pink color that we actually did. And now, great little question here. At a certain time during the titration, the rate of appearance of O2. Remember, the rate of reaction is equal to either the appearance of the products or the disappearance of the reactants. They could be both related, all right? And that relationship, very important because this pops up all the time. That relationship is stoichiometrically related based on the what? The coefficients. So, at a certain time during the titration, the rate of appearance of O2 was 1 times 10 to the negative 3, 0.001. Okay, what was the rate of disappearance of MnO4? Negative, at the same time. Okay, well, what's the ratio? Well, the rate of appearance of O2, okay, is 5 moles. The rate of disappearance is 2 moles. So what do you know? What do you know about this? What's the ratio? Right, so permanganate is it loses 2/5 of what O2 gains. Now if you don't see that, okay, you don't see that, if we're relating it back to O2, you can do this. Okay, 1.0 times 10 to the negative 3, we all know it's 0.001. And this is O2, right? Watch how I relate this. I want to get rid of my O2 to get my what? Permanganate ion. And what's the ratio? 2 to 5. Do you see how I'm grabbing that? Some people can see it right away. But if you're doing this, if you have the rate of appearance of the oxygen, now you're going to have the rate of disappearance by the permanganate. So all I got to do is times this by 2, very simply, and I get clearly, hope we can do this answer, this is 0.001. I know we don't have a calculator, but you can do this. So this becomes what? 0.002, right? This is 0.001. I'm timesing it by 2, okay? Now I'm going to divide it by 5. I need a calculator. No, you don't. Okay? Isn't this really 20 divided by 5? Yeah. Now it's not going to be 4 here. The 4 is going to be over here, correct? So that's going to be equal to 0.00 because this was 20.04. That's it. Which is the same thing as 4 times 10 to the negative 4, which is choice B. So yeah, I know we don't have calculators.
Choice D.
What's that?
Choice D.
It is D because I can't read. I want negative 4. Okay. Thanks for helping me out there. So yeah, 4 times negative 4, I just can't write the same answer. All right. So rock on. Okay. So yeah. So you had to do a little bit of stoichiometry. Really helpful to see what you're relating it to. They gave you information about O2, getting the permanganate, and just doing the simple math. They're never going to give you crazy math numbers. Okay, 33. Which element is being oxidized during the titration? Okay, now what is oxidation? Leo the lion says grrr. Okay, so if we're going to do this and wipe this out, wipe out. Okay, now Leo the lion says grr, so gaining electrons is reduction and losing electrons is oxidation. Why did grr first is beyond me, but hey, I'm tall. So we need to find who is losing. If you're losing electrons who are negatives, that means your charge is going up. Now if you're not sure, okay, you can just do trial by error. Mn is +2. Evaluate your MnO4. This is an important skill that keeps popping up. This whole thing is -1, so I do bottom numbers -1. If the whole thing was 0, bottom numbers have to equal 0. So here's what I'm going to do. There's 4 oxygens. I know that oxygen loves to gain 2 electrons, become -2. If I look on the periodic table, I see O, I see F, and I see neon. That tells me that oxygen likes to gain 2 electrons to become stable like neon. You're not going to see oxidation states listed on your reference table. Feel bad, now I'm over it. So -2 individually times 4 is -8. This has to be +7 for the manganese. +7 going to +2. Hey, +7 going to +2 is going down. That must mean you're gaining negatives. That's reduction. So that means that permanganate is out. Now, I'm looking at the O. What's the charge of any standalone element? Rhymes with 0, exactly.
0.
0, perfect. You guys are rappers. Okay, now, I see O going to 0. So let's check out O in what? Hydrogen peroxide. Now, some people like to remember, I can't speak, remember or memorize that in a peroxide, oxygen is -1. I don't think it's necessary. Hydrogen only has 1 electron, so it loses 1 to become +1. There's 2 of them overall, so it's +2. The bottom number is 0 in this case because it doesn't have a charge. This has to be -2 overall due to all of the oxygens. Each oxygen is -1, and there's our answer. An O -1 becoming an O0. My charge is going what? Going up because I am losing electrons, and I put that 1 electron here. So they're looking for oxidation where I'm losing electrons. Notice I put the electron on the product side so that both sides of my half reaction have a 0 charge. Notice they weren't asking for a half reaction. I'm just giving it because I'm showing off. So it's going to be the O -1 to O0, and that's why A is the answer. Or if we're learning this, okay? 34. Which of the following best describes what happens to the pH of the H2O? I can do this. Okay. Now, what's happening to the pH? Well, what's happening to me here? I can't move this baby. Okay. So what's happening to the pH? Well, as the reaction proceeds, I notice that, yes, I'm producing some water, but more importantly, aren't I losing my protons? Aren't protons being consumed? Yeah, so therefore, if I'm losing protons, the pH is going to do what? It's going to rise, right? So the production of the water, nah. H2 charge, nah. The H plus ions are consumed, right? We're losing our protons. So therefore, the pH has to rise. That's your best answer. Okay, so the solution becomes less acidic. 34 is cut. A C. All right, 35. The BF3, it's the best friend, multiplied by 3, I guess. Molecule is nonpolar, whereas the NF3 is polar. Which of the following statements accounts for the differences in the polarity? My gosh, look at the answer. Look at the choices here. They think you know nothing. They do. They think you know nothing. In NHF3, HF is joined to an N with multiple bonds. Why would a multiple bond affect the polarity? It's got nothing to do with if you got a singular polar bond. It's got to do with the what? The three-dimensional arrangement. Okay. So we're getting rid of NF are polar where these are nonpolar. Well, that's not even true, but even if they're polar or nonpolar, it's about the three-dimensional arrangement. There are scenarios where things that have nonpolar bonds only and can be polar because of their what? Three-dimensional arrangement. Ozone, little fun fact, has all what? Nonpolar bonds, but because it's a bent molecule, that creates polarity. Too much info, I know. NHF3 is ionic. Non-metal. Okay. So D is the best answer. Unlike BF3, NF has a non-planar geometry. Now, I want to kind of just do this real quick because it could be a part 2 question where they say draw it or prove it to me. So whatever is on multiple choice is certainly game. Okay, just like, I don't know, ducks in a pond. But the point is, NH3, NF3, not your best friend 3. What does this look like? Well, N has 2 lone pairs, and then you have the F. What is the hybridization here? What is the hybridization here? sp3 with a lone pair. This lone pair does what? Pushes these bonds that were in a nice tetrahedral formation downward into what I said, basically into this what? Top of a 3-sided pyramid. So we go triangle pyramidal. So this is a top of a 3-sided pyramid. And these H's are being pushed downward into an asymmetrical shape. Very polar. Now we've got BF3. Now boron only has 3 valence, so you're going to make 3 F bonds. This, of course, is sp what? Thank you for saying quietly sp2. Someone was thinking it. I have my 6th sense working. There is 1, 2, 3 pairs of electrons around the central atom. That means an S and 2 P's came together. Okay. Now, what's the shape of this? This is triangle planar, right? This is sp3 because we have what? 1, 2, 3, 4 pairs, and this would be the tetrahedral shape with the lone pair. We consider just that area. So this is planar. The reason why this is nonpolar is because, as I love to say, it is equal in its unequalness. So it has 3 polar bonds, but they're equal in all direction. I know I overtaught that, but these are things you can see in part 2. Number 36, classic question. Classic. So you will see Q versus K in so many different ways. This one is an obvious question. So at a certain point in time, a 1 liter rigid container has these amounts of moles of gases. Okay, now you notice it's in 1 liter, so I can get molarities pretty simple. The molarities are the moles because mole over liter. Which of the following describes how the measured pressure in the reaction will change and why it will change? Well, we have to know what the Q is. They're telling us this is a reaction quotient. This is some place in time where we have these. And as I always love to draw, this right here. Here's my K. I don't care if it's KC, KP, KP, KA, KB, KW, AOK. It goes right here. Now, what's the Q? Well, Q is equal to products over reactants, coefficients become exponents, solids and liquids don't apply, they're all gases. So what's my Q? My Q is going to equal to my product, PCl3, which is 1.5 to the first power, over the reactants, The reactants is PCl3, which was what that was. Thanks for correcting me. Okay, so this is, let's just write it out because I'll make mistakes. This is PCl5 over PCl3 times Cl2. Now that I've slowed myself down, okay, let's put the values in. All right, to my Q. So PCl3, as I said before, PCl5, where are you, is 2.5 molar. Mr. Grotsky, it's moles. How do you do molar? Well, it's moles over liter, so it's the same thing. So 2.5 goes on top. On the bottom, I have PCl3, and that's 1.5. And I'm timesing by my Cl2, which is 1, to make some tough math here. So 2.5 divided by 1.5 times 1, hopefully we'll see it's 2.5 divided by 1.5. Now, I can't do this in my head. You don't have to. All I gotta know if it's bigger or smaller than K. By the way, what would be, if this was 2, wouldn't this be what, 3? Right, so the Q, by estimation, is some number between 1 and what? Or 1 and 3, right? 1 and 2. Somewhere between 1 and 2. I can do the math. So the Q is equal between some number between 1 and 2. What's the K? 6.5. So the Q is some number between 1 and 2, which is what? Q is less than K. It's going to go forward. Now, if it goes forward, look what we have here, party people, for the millionth and one time. We have what? 2 gases combining to make 1 gas. So because it goes forward, not a tremendous amount, but as it goes forward, we're going to lower the pressure because we're going to lower the total number of gas particles, and pressure is due to gas particles. So the pressure will decrease because Q is less than K. I have seen this problem, something like it in many different fashions over and over again. Something to definitely cash in and cha-ching. Okay? Full of sound effects.
Oh, see when it's backfired.
Okay. Now, let's look at this problem once I get rid of this stuff. Maybe. Like my computer's not happy. Could be the 25 tabs I have open. Okay, so I've got a reaction. Oh my God, so much information. So much information. I'm giving up already. No! Consider the reaction represented above. When equal volumes of N2 and H2 each are at 1 atmosphere, are mixed in a closed container, there's absolutely what? No NH3 being given off. What does this tell me? The reaction's not going forward. Why is it not going forward? It's no. Look at the spontaneity. Delta G is negative. Spontaneity has nothing to do with the rate of reaction. How fast the reaction goes has nothing to do with how negative delta G is. This is spontaneous. It is very negative. But what do we have with all reactions? Okay? We have, this is an exothermic reaction, correct? So if I was to draw a potential energy curve, it would look something like this. High going to what? Low. What is preventing my reaction from going? This little bump here. The activation energy. We have gasoline sitting in a container. Doesn't it like to react with oxygen and burn? Absolutely. Is it reacting? Probably a little bit, but not enough. Okay, it's just sitting there until you add the what? The spark.
This piece of paper.
Okay, to overcome. All right, so the reason why your papers aren't burning right now is because of that. So all that question was that a high activation, it makes the forward reaction extremely slow. It's about the activation energy. Okay? And we all should know when R, this is a little aside, R equals K times the, let's say the reactant, A, whatever it might be. This equilibrium K is tied to something I like to call activation energy. We write in big boy and big girl chemistry as E of A. So the higher the what? Activation energy, lower the what? The K value. Okay, that's called the Arrhenius question that we looked at. Not needed to know that, but you should know that, okay, in terms of that relationship. Okay, that was a lot of fun. Oh, yes! You bet I love the titration. Yes! What do they want? They want the pKa of the acid, and they want the concentration of the base. So they want two things. They want the pKa, or we say pK, and they want the concentration of the hydroxide. Now, what do we have? We have some acid, okay? So data collected. Notice we're adding what? Look at this curve. What are we adding to what? pH going up or down? It's going up, so we're adding drops of Jupiter. In those drops, what are we adding? Right, so we're adding hydroxides into acid. Great. However, in this experiment, we already know the concentration of the acid. They told me the acid is 0.1 molar. And they told me that the solution is 20 milliliters. Okay. What's the concentration of the base? Where is the equivalence point? Find your asymptotic line. Don't be an asymptote. Find the asymptotic line.
It's basically 20.
And
20.
yeah, I would say right there. So it's basically, for the pun involved, good job, you get 20 milliliters. This is a tough problem. Check it out, party people. I have 20 milliliters of a certain concentration of an acid. I need exactly 20 milliliters of the base to neutralize it. What could be the concentration of the base? I'm throwing my entire career out there and saying that it's 0.1. Okay, now if you like MV equals MV, I'm not a big fan, you could have solved for that. Or if you wanted to, because you don't have a calculator, use the math, you could have said, okay, 0.020 liters times it by what? 0.10 molar. Liters times molarity always gives me moles. I get point what? 002 moles. And then you divide that by what? The volume of the base that was added, which is what? 0.02. And you could see the math is pretty simple. It's 0.1. Or you could have recognized that right away. So that's the first part. Second part, how do you get the pKa? Well, here's the buffer region. If it took 20 milliliters to what? Titrate it, halfway titration is what? 10. Now, why am I doing this I call max buffer position? Because I have equal amounts of what? I'm going to have my weak acid. I'm going to produce my conjugate acid. If I half titrate the acid here, I'm going to have equal amounts of these guys. Okay, you should know this. This is my third practice test I've gone over this way, so I shouldn't have to explain it, but if this is your first one, okay, you have to know that when you half titrate something, that means I had what? I did not add enough what? Base to neutralize all of this, but whatever base I did add forced the production of the conjugate base. All right, since if I was to make this 2 moles of acid in my beaker, and I added 1 mole, you can all see this is a 1-to-1, all right? I would lose 1 mole, and I'm left with what? 1 mole left. This would go bye-bye, and I'd produce 1 mole of this with 1 mole of acid. So what does that mean, party people? That means that when I use the Henderson-Hasselbalch, and I'm sorry if you understand this 5 minutes ago, but cool if you do. Henderson-Hasselbalch takes pH equals the pKa for the millionth time and 1 time. Log of the conjugate acid, A minus over what? HA. This is going to go to 0 because if I have equal amounts of these guys, okay, at the half what? Half neutralization point, the log of 1 is 0 and my pH equals my pKa. All you do from that max buffer position, I know I'm not drawing a straight line, but try to find that value. Okay, what's that pH there? So, my gosh. So our pKa is 4.7, and that hard math problem, the concentration of the base is 0.1. You'd be surprised. How many people get this question wrong? Okay? And how many times have you seen pH equal to pKa if you're doing what I asked? Okay, whoa, heating, cooling curves. Okay, this is back some basic chemistry, although there's no acid base here. Now, this question is all about conversions. This is all about conversion. This is a conversion question. Part 2, somewhere in your part 2 or your multiple choice, they love to do conversions. So what they said was, how much energy is required to melt 64 grams of methane? 64 grams of methane. Now you needed to realize that this is heat of vaporization. I just burped and I think hiccup at the same time, so it's kind of weird. So that's called a hic burp. I'm not sure. In any case, all right. You're laughing at my social incompetence. I'm sorry. I made a scene. All right, now, so heat of vaporization, heat of fusion. This is melting. This is solid, liquid, gas. Crazy amount of energy. So this is solid going to a liquid. This is melting. They gave me 64 grams of methane, party people. Look what they give me. Look at the units. This is kilojoules per mole. So I got to convert this to mole. Hello. They were nice enough to give us, methane is CH4. Methane, they gave us that the formula mass of methane in the problem was what? 16. I don't know why they did that. I think we know that because we go to the molecular mass party and memorize these. But hey, if you missed the last one, you're a loss. So there's 16 grams per 1 mole.
I can't do this, bro.
Yeah. 64 divided by 16. You got it 4. Okay, you used a calculator. I saw you. You had the Apple. You had the Apple Watch.
You're a cheater.
Oh, I would have tried Apple.
Sam doesn't even have an iPhone.
That is not true. 60 times 2 is 32. 32 times 2 is 64.
Sam told me. Yes, 16 times 2 is 32.
Sam
Yeah.
couldn't even have an Apple Watch. He has a Samsung.
Oh,
What is happening?
I guess that falls in line of rubber on blue. I don't know. That was a great comeback. Okay. So we've got 4 moles.
That's like normal. That's like normal for our class. I'm making these kind of jokes.
So 4 moles. My gosh, what is the number? It's 0.94 kilojoules per 1 mole. So I'm going to, just because I'm cool and tall, I can know that this is almost 1. Isn't this almost 1? And if you ask Sam, he'll tell us 4 times 1
What is it, Sam?
is about 4. And I say about 4 because it's this. And it's kilojoule. Okay? So the only answer there, okay? Now, of course, only answer there it's about 4 is choice B, 3.8 kilojoules, okay? Because I'm getting emails from students, I can't do the math with the calculator. Slow yourself down, round off. Look at these numbers, they're so far apart from themselves, we can do what? We can estimate. So that was a converting problem. Number 40. Which of the following best explains why more energy is required for the process occurring at 110 Kelvin than the process occurring at 90? Well, if you don't remember, at 110 Kelvin, we've got a liquid go into a gas. Okay, tremendous energy right there. So the problem is that we've got a phase change, heat of vaporization. And what we're doing is, in order to become a gas, the liquid molecules' intermolecular forces have to be totally overcome, because gases, especially if they're acting ideally, like Tahira, is that we, okay, a little shout out to my videos here, we need to overcome these to become a complete gas. So you have to overcome what? Intermolecular forces. Okay? So the intermolecular attractions are completely overcome during now, are they?
Please do that.
Almost. The solid phase, they're weaker? No, they're stronger in the solid phase. Electron clouds of methane are less polarizable at lower temperatures. That's crazy. And vaporization involves a large increase in temperature. This would be nice if it said large increase in what? Energy, right. Temperature Q is not equal just to T. It's MC change in T to get to Q, so it's not. So A is the best answer, talking about overcoming intermolecular attractions. Now, of course, they said completely overcome. In truth, gases have some attractive force, so I'm not loving the answer entirely, but it's the only choice about intermolecular forces. And I can't say enough, party people, when I'm talking about melting, boiling, any phase change where you're not breaking bonds, do not talk about bonds broken. When they talk about why is the boiling point higher than this, you're going to get that question Monday, somewhere, somehow, when they're asking you to discern between boiling points or melting points. Do not mention bonds. You're talking about attractive forces. Although they didn't have a choice here, I needed to mention that. Okay? And now we have the lacrosse player hitting my wall here, because we're not doing anything important. Okay, 41.
I can tell you.
That's okay. It's not funny.
No, let's hear her do it. Let's
Is that
hear her do
bugging
it.
you?
Yes.
Okay.
Let's
Go
do
fight
it.
him.
I
Me
want to
too,
win this.
people?
I really want to win.
No, let's hear
Yeah, I
it.
want to watch. I just
I
want
just wanna watch
I
the
just want to
video.
win it. I just want to watch the other.
Alright, so I'm not going to pause this.
Look at all them go.
Right now.
When Tahira, no, when men literally chase Tahira, you're the only civilized.
Oh,
That's
true.
fun.
Alright, so
Oh,
41, I'm going to keep going
Alex.
since I'm rolling here. The enthalpy of vaporization of water is 40.17. Okay, you can tell people really want to be here. Which of the following best explains why the enthalpy of vaporization, I can speak, of methane is less than that of water? Why does it take less energy? Okay, think about it. The enthalpy of vaporization of water, that means the energy required to completely vaporize a mole of water is 40.7. Which of the following best explains why the enthalpy of vaporization of methane is less than water? Well, why would it be lower? Because it's easier to separate methane. Its intermolecular forces are not as strong, so it takes less energy. Now, what does methane, or what does water have that methane does not? Water has these electron deficient H's, otherwise called H bonding. Or as I like to say, H bonding. So, methane does not exhibit hydrogen bonding. Okay, but you say, Mr. Grodsky, methane has what, a carbon and 4 H's. I see an H here. Okay, so why wouldn't this H of one methane molecule get an H of another? Because this carbon to hydrogen H is not electron deficient. It's got to be bonded to a FON, having FON with H bonding. Okay, this is essentially a nonpolar bond. Okay, so A is the best choice. All right, going on to 42. Okay, as you notice, we're seeing consistent type problems. You're seeing a PES question, a photon emission spectroscopy question. We're seeing questions usually with a mass spectrometer. We're seeing questions with, in this case, an alloy question. Or I'm thinking of another one that I can't think of off the top of my head that are coming up in almost every test. Okay? So here's an alloy question. And what you have to realize is in this question they're giving you some information, but the stuff to the left is the key. Notice we're making an alloy with iron. It's stainless steel. This is chromium, nice chrome wheels, okay? Especially the spinnies in Riverhead. Now, the point being is that we have iron and chromium both have the same what?
Cool.
Approximately the same molar mass. That's not the key on it. I mean to circle those, okay? They have approximately the same atomic radius. That's the key, not these guys. So when you put them in, this is going to be called a substitutional alloy, because chromium can take the place of where iron is. If I look at my choices, where is it where I have chromium getting in between because it's too small? Look at C. I'm going to get rid of C because chromium, okay, is about the same size of iron. It would take the place. It wouldn't go in between. So that's why C is gone already. Now, where would carbon go? Well, carbon, for the same reasons, is smaller, okay, in terms of what? Its atomic radius. So with the carbon, we make steel, we use carbon, and carbon goes in between the irons and or the chromiums because it can fit in there. We call this an interstitial alloy, but we're putting both of these together. And what the question is really reading is, which of the drawings is correct if I have a scenario, and they're telling you this in the problem. The reason why it's called stainless steel is because it doesn't rust. The chromium atoms get oxidized by the oxygen and form a non-reactive layer of what? chromium oxide. So that's the chromium metal with an oxygen. Oxide just means a salt on the top layer. And they say that this layer prevents the rusting. So the surface choice, the top layer choice, has to show chromiums and oxygen, okay? And notice oxygen is what? Very small radius. I keep doing the molecular mass. Has a very small radius that's very similar to the what? Radius of the carbon. So the oxygen will get in the crystal a little bit, but it's only going to be at the surface. It makes a protective layer. There's going to be no oxides inside the compound because the oxygen can't get there. So if you look at where else we have a nice possible answer, D, here's chromiums, and here's the oxide layer, but having, okay, and that's a possibility, okay, but you notice on the inside, this right here, we're seeing oxides. So if you see the inside layer having oxides, that makes no sense because the oxygen can't get inside the metal. So C and T go bye-bye. And if you notice, A isn't showing any chromiums, okay, in the surface layer. So B is the best answer. Why? Because the O and the Cl take up spots in between. The top layer has that protective layer of chromium oxide. There's no oxides in between. Okay, we have some carbons, and the carbons give the steel the strength. Why do the carbons give the steel the strength? Why is there more hardness in the steel? Look, here's my iron, okay, and here's my iron. And if I have an interstitial alloy, this has been popping up, and I'm not a great drawing, but if I have my my carbon being added in the middle, and I hammer down on this, even though I didn't draw it really well, okay, it's hard for this iron to be cleaved because it's going to hit this little guy in the middle. So it gives it hardness, okay? Any case choice, whatever question that was, 42 was choice P, okay? Oh my gosh, so many people got this wrong, okay? So many people got this wrong. How many times are they going to ask you whether something is first or second order? They can only ask you that with graphs, okay? In the reference table, they give you two formulas that are integrated formulas. They give you the ln of A of some time 0, okay, minus the ln of A some 0 equal negative KT. Now, if you rearrange this and make this positive, this is how they give it to you. This is the first one they give you. So this is for first order. So if I rearrange this, ln of AT equals negative KT. I'm just going to add plus ln of A of both sides. A of 0. What do I have? Y equals mx plus b. This right here is the ln of A at some initial concentration, and any point along this point is some ln of A at some time period. Notice the slope is what? Negative, it's going down. Notice it's a what? Straight line. In your reference table, this is the first one they give you. That's why choice B is the answer first order. Now, if this curve was bending, okay, it would not be first order. That has to be a straight line. Now, what is the only other possibility? Sometimes they ask you to what? Draw this, if it's first order. If you knew it was first order, they ask you to draw it with the correct what? With the correct y-axis. This is a really easy problem. Sometimes they ask you to draw this. Now, if it was second order, okay, they'd be written like this. 1 over A of some time period minus 1 over concentration of A at some initial is equal to positive KT. When I rewrite this, it becomes 1 over AT equals KT plus, just doing some math here, plus, I can write it, 1 over A0. And what would this be? Y equals mx plus b. This is the second one they give you. So this is for second order. Notice the slope is what? positive, so this would go look like this if it was second order, and my y-axis would be labeled 1 over A. You're going to see that. That's a point or two on this test. That's really simple. But this is first order because it's giving me a negative slope and it's linear. Okay? All right, so I think that's a pretty straightforward question.
So why do you think people got it wrong then?
Because for some reason, they get all crazy when they see natural logs. They get all crazy with that formula, with the natural log. I think they get intimidated by so many of these questions, like, oh my gosh, there's a natural log of something. When that all it is just that y equals mx plus b. They give you that in your reference table. Okay? So really nothing to be intimidated about. The hardest question on this multiple choice I thought was the equilibrium one, where you had to times it by 2 and realize that. But again, practice, practice, practice. These are the same kind of questions. Okay, here we go with this. The equation represents, the diagram shows two profiles, path 1, path 2, 44. Which of the following most likely counts for the difference between the reaction path 1 and reaction path 2? Okay, now first of all, some basics here. Okay, this is a potential energy curve. Number 1, it's endothermic. We're starting low and we're going high. This is my delta H, the difference of where I start and where I finish. Who's tapping their foot? All right. Now, stop. Now, so my delta H is positive 50. Now, the difference between path 1 and path 2 depends upon usually a catalyst. A catalyst will start a whole series of steps, a brand new mechanism that wasn't there without it. So it's not about temperature, okay? This is measuring different, basically different heights or different barriers to start the reaction, or I should say different activation energies. This is the activation energy to overcome this barrier for the reaction to occur. And of course, this lowered path is the lowered activation energy. Now, activation energy is labeled E of A. Okay? Use that to your advantage if you see that. Now, so it's not about temperature, because at higher temperatures, okay, more energy is available. This will happen regardless. We're lowering the energy needed to start the reaction. So what accounts for the path? Well, we should realize that a catalyst, okay, provides a reaction pathway that's totally different, and the combined activation energies of all the individual steps are going to be lower. So the presence of a catalyst in path 2. Now, I like writing it like this. If there was a two-step mechanism, it might look like this. And you could just measure the individual activation energies and add them together, and it would be overall lower, except my drawing was not really drawn to scale that way. So understand that a catalyst starts a mechanism, and that mechanism means that the combined new steps creates a new set of reactions that is overall lowered. By the way, I always say to my first year chem students that this is the non-medicated hump, and this is the medicated, right? So this is the what? The medicated hump, or this is the unmedicated hump, uncatalyzed, unmedicated. If you got a hump, you should catalyze, you should medicate it, right? And this is the medicated hump. Okay, enough said.
Just imagine that.
You got a hump, get some medication. 45. Which of the following best describes the flow of heat when 1 mole of X2 decomposes? So what they're asking you, can you realize that this is the enthalpy, the difference of where you start? And by the way, if you didn't notice that, the potential energy of the what? Products minus the reactants gives you a positive value. That's what delta H comes from. So it's positive, it's endothermic. That means energy is what? Being taken from the environment. Now, why is it 50, not 100? 100 represents the activation energy of the catalyzed reaction. They're making you realize that delta H was 50. So 50 joules of heat are transferred into the surroundings. That'd be released. That'd be exothermic. 50 kilojoules are transferred from the surroundings. That means it came from the surroundings. It was consumed or absorbed. B is the answer. Okay, so not very difficult, but making you look at potential energy curves again. And here's another delta S question. I like this. You're going to see questions like this, 46 definitely. Okay, in 46, the reaction is thermodynamically favorable. Okay, now, what does that mean? Delta G is equal to what? If it's thermodynamically favorable. You gotta get this down. Delta G is positive or negative? Negative, correct. Now we know delta H is what in this problem? Positive. Now let's check out my formula. Now you probably can see this right away. For me, I've got to do this. Delta G, which has to be negative, is equal to delta H minus T delta S. That's what delta, one of the ways delta G is equivalent to delta H. Now, this is definitely positive. Minus what? Well, this better be what? It better be positive. Why? Because by putting a positive here, and I do plus a negative, this must be positive enough, and because of the negative sign, does what? Makes this negative enough to overcome this positive delta H to make this negative. So it can't be equal to 0. It can't be equal to delta H because that would be 0. If this was 0, delta G would be positive, right? If this whole expression was 0. If delta H was, if this was equal to delta H, then delta G would be what? Positive. So this value has to be greater than delta H. Some people say, what's this divided by 298K? We'll just print this T on the bottom, that's all. But the bottom line is, this value has to be big enough in entropy, positive, to overcome this bad enthalpy. Why is this bad? We're taking energy from the environment to go into a reaction. That is bad in terms of the second law of thermodynamics, because you're making the gas particles now go slower. But if the system in the reaction is increasing the entropy enough to overcome this bad event, then the process will work because the overall entropy of the universe increases. So in any case, if you didn't like that, and some people still don't like that T, watch what I do here again. Solve for S, delta H, okay, minus delta S. And if you just think about it, this has to be a big enough positive. This is a positive value, okay? This is to make this be a big enough negative to make delta G negative and make it thermodynamically favorable. That's why C is the answer. Some point of that will be picked up. Okay, 47. Probably overtaught that again. Okay. Oh my gosh, we just did this? No. Looks very simple. Looks very similar. I can't speak. Too many review videos. 47. Which of the following diagrams best illustrates how a displacement of an ionic crystal results in a cleavage, which means a splitting, and brittleness? Okay. You guys know ionic compounds can be split, and the reason is right here. If you hammer down on a crystal that's ionic, you could put two negatives in close proximity. These guys are going to what? Repel and break apart. This, okay, is showing a scenario where after we're adding different, all of a sudden we're adding +2 ions in here. We're doping this. Okay, so this is not showing a cleavage, it's showing just the doping of ions. Don't be a dope. And C, this is a good one. C is showing metallic bonds. This is showing the reason why things that are metals or metallic or have malleability or ductility, they don't cleave or break as easily, is because when you hammer them, these electrons are so loosely held, they buffer the nuclei in the crystal. So C would be showing why they don't what? Break. This is showing ductility. So this question could be C if they're saying which of the following shows why metals are ductile, that don't cleave, or not brittle, or the word are malleable. Okay, ductility just means you can draw them into wires because they are not going to break because of this, and malleability means you can hammer them and shape them any ways. But the best answer here is of course A, because brittleness is something else you should realize. An ionic crystal like sodium fluoride is positives and negatives equally interdispersed in a three-dimensional crystal? A is the best choice, and D is showing molecular compounds that, okay, are attracted by London dispersion forces, okay, and they have a little bump here. Okay. 48. 6 mole sample of C3H8 and 20 mole sample of Cl2 are placed in a previously evacuated vessel. How many times have they talked about a previously evacuated vessel and they put in gas? They're in love with gases, okay? So you'll see a question. When they react according to the equation above, after one of the reactants has been totally consumed, how many moles of HCl have been produced? Okay, so this is Jeopardy. No, this is a limiting reagent problem. Okay, sorry, I'm just losing it. Actually, I have lost it. Okay, now, so I'm going to do an ice table, a Stoich table. Okay, now, I'm going to kind of do it backwards. I've got 6 moles of this sample, and I got 20 moles. Now, what I do real quickly to figure out limiting reagents, I always keep it in moles. Now look at the ratio. It's 4 to what? 1. So I'm going to start with the one with the greatest number of moles. I'm going to lose all of that because I know that this one's going to be what? 1/4, right? The one with the greater number here, okay, this one has to be a fraction of that. That's one quick trick. This has to be 1/4, and we've seen that in another problem that we've just did, what? I don't know, 20 questions ago. These questions are very similar. So, I'm going to get rid of, I'm going minus 20, so I'm doing initial, change, and then at the end I'm kind of doing a backwards ice because it's written this way. Now I'm not going to do minus here. This is not going to be minus 20. If this is minus 4x, this is minus x. This is minus 20. This is minus what? 1/4 of 20. So this is minus 5. Right? Because it's 1/4. Right? It's a 4 and it's a 1. So this, after I subtract at the end, I'm left with 1 mole of this and 0. So this is my limiting reagent. It goes bye-bye. Now, why did I have to do that? I had to figure out who my limiting reagent was before I started the problem. Because if I picked C3H3 to do the stoichiometry problem, I would overestimate the product. Maybe you guys would have saw that faster than me doing this. Again, I'm showing you every piece of this. Okay, are placed in a previously evacuated vessel. Okay, now when they react according, after the reactants have been totally consumed, notice this is not equilibrium. It's called what? Completion, correct. We're going to drive it forward. How many moles of HCl have been produced? All right, well, I'm going to start with my limiting reagent, which is what? 20. And of course, look at the ratio. It's 4 to what? 4. So if I have 20 moles of my reactant, how many moles of my product? 20. But you could have done this, and they're very nice. Okay? But you had to figure out first who the limiting reagent. You couldn't assume. Is 48C? I can't believe they would do that. 6 mole sample, yeah, has to be. Okay? So they were very nice, so you didn't even have to consider the limiting reagent here, but I just feel like in another problem, okay, they would have picked, they would have had the non-limiting reagent. Because so you picked 20 because it was 4 to 4, but what if in some scenario this wasn't the limiting reagent? You would have gotten it wrong. So you have to go with the limiting reagent, okay? Or you can go with how much actually reacts. Look at this. 5 actually reacts, and this is what? Right, okay? So that's why 48 is C. It's an easy question. I went over limiting reagent. You probably could have gotten by without it by luck, okay? Oh my gosh, here we go with boiling points. They love, at some point, for you to understand. This you better have down. If they ask in part 2 for boiling points, do not say it has stronger intermolecular forces. That's too vague. You have to explain. They want you to explain all the forces. I know this is a multiple choice question, but you could see these 3 on part 2 and explain. Like, consider this. So let's put this in order of lowest to highest boiling point. How am I going to do that? I'm going to identify the attractive forces. I see some O's here. This gives some polarity, doesn't it? So this not only has dispersion forces, LDFs, it's got dipolar forces. This is only hydrocarbons, which means I know that it's only nonpolar. So this only has LDFs. Now, why are they giving me the molecular mass? There's a link to molecular mass. The link to the molecular mass is a link to essentially how many protons you have, which is linked to how many electrons. By giving you similar molecular masses, they're saying to you that you have similar number of electrons about, okay? So that's how it works. So they're telling you that all of these have similar LDF forces. And you should be explaining these, okay? So why is butane going to be the one that's lowest? Because it only has what? LDFs. Now what does acetone have? Acetone, with itself, has LDFs, but also has what? No. It has dipolar forces. What does that mean? It's got a negative end and probably a slight positive ends. This is a polar molecule attracting. It does not have any H's that are bonded to a what? FON. It does not have any electron deficient H's. So this has no what? H bonding. Now what does 1-propanol have? It's polar, so it's got dipolar forces, correct? But what does it have? The other two don't. Right, this H is electron deficient, so this one has LDFs, dipolar, and H bonding. So if you were to tell me, list these in increasing boiling points, you would say butane. Who else? Acetone, because it's got less forces. And then the one with the highest is the one that's all three, 1-propanol. And if they ask you the differences, tell them, talk about the other ones. Propanol, it's not so much that propanol H bonds is the only reason. It's that propanol has more attractive forces, has an additional attractive force, correct. And I'm telling you, you're going to see that, okay? And so the answer here is B, okay? And last one in the multiple choice, okay? And my gosh, a real easy question. They give you a lot of information. The reaction represented above occurs in a single step. Okay, because I know that, the coefficients become the orders. Okay, but that doesn't help me. Okay, between the particle of NO and NO2. We would call this, my friends, a bimolecular collision, right? Two of these collide. When one thing breaks apart, it's unimolecular. So sometimes you'll hear that word. Anyway, a scientist, oh my gosh, correctly calculates the rate of collisions between them two and has sufficient energy to overcome the activation energy. They're telling you that it's occurring. The observed reaction rate is only a small fraction of the calculated collision rate. So we have enough activation energy, yet it's barely going. So what must explain the discrepancy? Well, this is called collision theory, something you learned last year. In order for a reaction to go, you must have an effective collision. What's an effective collision? The first priority is you have to have high kinetic energy, which means high energy has to be given so that the colliding molecules overcome their repulsive forces, which is the cloud of electrons. This is activation energy. You must have high enough energy to slam to either break bonds or create them. That's activation energy. And the second one people forget, and that's what this question is, especially for big molecules, is you have to have proper orientation. Why is that? Well, in big molecules, there are going to be places where bonds can be broken and where they can't be broken. Case in point, you guys learned about pi bonding. In a hydrocarbon, where you've got this double bond occurring, single bond between, let's say, a hybridized orbital, and then you've got the what? The pi bond occurring here, above and below. Pi bonds are easily broken because they're a little farther away from the nucleus. A particle that's going to bond with this carbon has to hit this pi bond. If it doesn't, it's not going to react. So I always call proper orientation kind of like my family at a reunion. We're not good dancers, and the chance of an elbow-to-elbow collision is slow. So the elbow-to-elbow collision would give you the proper orientation. So, any case, the answer to this question is, which of the following explains why, even though we have enough kinetic energy or activation energy, they must collide with the proper orientation. They have to hit their active sites. Okay, that's why B is the answer. All right? So we're done with this multiple choice. I will post it with the second half. I will link it because I have nothing else to do in my life. All right? But that shows you the second part. For those that weren't here yesterday, the 1 through 25 is also posted, and I'll put this all together.